Hi students, welcome back to this course, an introduction to mechanical engineering. I am Professor Yao. Stress-strain curve. The keywords: stress-strain curve, stiffness, Hooke's law, so forward, a property of material, the stress-strain diagram. Proportional limit, elastic modulus, Young's modulus, elastic limits, ultimate strength, fracture, yielding, yield strength. The definition of stress and strain, in contrast to force and elongation, are useful because they are scaled with respect to the rod size. Stiffness. For each individual rod, however, the applied force and elongation would be proportional to one another, following F equal K times delta L, where the parameter K is called the stiffness. Hooke's law. The observation is the base of the concept known as Hooke's law. The power of any spring is in the same proportion with tension thereof. That is, if one power stretch or bend one space, two will bend it 2, and 3 will bend it 3, and so forth. Stress-strain curve. The stress-strain curve, the stress-strain relationship is a property of the material alone. Elastic and plastic regions. The stress-strain diagram is broken down into two regions: the low strain elastic region and the high strain plastic region. Proportional limit. For strain below the proportional limit, point A, you can see from the diagram that stress and strain are proportional to one another, and they therefore satisfy the relationship. Elastic modulus. The quantity E is called the elastic modulus, or Young's modulus, and it has the dimensions of force per unit area. The rod elongation, when it is loaded below the proportional limit, is delta equal FL over EA, with the stiffness K equal EA over L. The elastic modulus of material is related to the strength of its interatomic bonds. Elastic limit. In a strain stress diagram, point B is called the elastic limit. For loading between point A and B, the material continues to behave elastically, and it will spring back upon removal of force. But the stress and the strain are no longer proportional. As load increases further beyond B, the material begins to show a permanent set. Yielding. Yielding starts to occur in the region between B and C, meaning that even for small changes in stresses, the rod experiences a large change in strength. In the yielding region, the rod stretches substantially even as the force grows only slightly because of the shallow slope in the stress-strain curve. For that reason, the one set of yielding is often taken by engineers as an indication of failure. Yield strength. The value of stress in the region BC defines the material property called the yield strength S sub y. Ultimate strength. As the load is increased even further beyond point C, the stress grows to the ultimate tensile strength S sub u at point D. That value represents the largest stress that the material is capable of sustaining. Fracture. As the test continues, the stress actually decreases owing to a reduction in the rod cross-sectional area until the sample eventually fractures at point E. Material testing machine. The keyword. Material testing machine. Load cell. Extensometer is drawn on a graph. Aluminum and other non-ferrous metals. 0.2% offset method. The slope of the curve. Material testing machine. Stress-strain curves are measured on a device called a material testing machine. During tension testing, a specimen such as a rod of steel is clamped between two jars that are gradually pulled apart. A load cell that measures force is attached to one of the jars, and a second sensor called extensometer measures the amount that the sample is stretched. A computer records the force and elongation data during the experiment, and those values are then converted to stress and strain. When the stress-strain data is drawn on a graph, the slope in the low strain region is measured to determine E, and the value of the stress S sub y at the yield point is read off the curve. For aluminum and other non-ferrous metals, the yielding point and the narrow yield region BC are generally not seen in the stress-strain curve. 0.2% offset method. For such cases, a technique called the 0.2% offset method is instead used to define the yield strength. The elastic modulus is determined from the slope of the curve at a low strain, and the yield stress is found by using the 0.2% offset yield method. Homework. Handwriting all keywords and submitting them to Coach Facebook. Just do the online quiz. See you next time.